In this screencast, we discuss the topic of function notation. You've seen that input and output variables of functions are generally represented by letters. In addition, we often assign letter names or labels to the functions themselves. Remember that a function is a process. A function is not a variable. So we are talking about giving names to the functions, to the processes. Why would we do that? Well, if we happen to be working with many different functions simultaneously, it's handy if each function has its own name and a short name, like a letter name, so that we can quickly and easily reference the different functions. Suppose, for example, that we happen to be comparing 3 different population projections over time for a certain community. Each projection is described by a different function shown below. So I have 3 different projections. Each of these projections is described by a different function equation. We'll assume that t is a time variable measured in years, and p is a population variable that measures people in thousands of individuals. So you can see here we have 3 functions, and all 3 functions use the letter t for the input, and they use the letter p for the output. These are functions that are designed to allow you to insert a particular year in time, and the function outputs a predicted population value for that year. Now, the 3 functions give you 3 very different predictions. We have an exponential projection, a linear projection, and a quadratic projection. If we were going to compare these projections, it would be nice if each of these equations had their own label or their own name. So for the exponential projection, we might assign the letter E to that function. For the linear projection, we might assign the letter L. For the quadratic projection, we might assign the letter Q. So anytime I say Q, you know that I'm talking about the quadratic projection. If I say E, you know I'm talking about this function right here. So these letter names help us identify which function we're talking about. Now suppose that we want to compare the values of these population functions after 10 years. In other words, we want to evaluate each of these functions when t is 10. So for the exponential projection, if I insert 10 for t, what I find is I get an output of 8. For the linear projection, if we insert 10 into the equation, we find we get an output of 16. For the quadratic projection, when we insert 10, we find we arrive at an output of 14. Now, these input-output pairs here are very cumbersome to write down. If we use function names or labels like E, L, and Q, we can express these evaluations or these input-output pairs more simply. The notation we adopt is the following. We simply write the name of the function, that would be like E or L or Q, and then behind it, in parentheses, we write whatever we're putting into the function. Whenever you see the name of a function followed by parentheses and a quantity inside the parentheses, this is our way of writing the output of that function, assuming this input. So function name followed by input in parentheses is equal to the output. So for example, Let's look at the exponential projection that we made above. When we insert 10 into this function, we arrive at an output of 8. Now for the exponential projection, that was given by the letter e. That's the function name. So instead of writing when t is 10, p is 8, we could write this more simply as follows. I write the letter e for the name of the function. I follow it with parentheses, and inside the parentheses I have the number 10 because 10 is what we're putting into the function. When I write e followed by the 10 in parentheses, this is our way of writing output. This is the output of the function e when 10 has been put into the function. And so we say that that output is equal to 8. Now let's look at the next projection, the linear projection. We know when we put 10 into the linear function, we get 16 coming out. The linear function has a name L. That was what we gave it. So I could write this statement right here as follows. If I take my function L and I substitute 10 into the function, there's the input, the output is equal to 16. Finally, for the quadratic function, instead of writing when t equals 10, p equals 14, I express that fact as follows. I use the letter q, referring to the quadratic function. I put 10 behind it in parentheses, meaning that I'm substituting the number 10 into the function q, and the resulting output, that's the quantity I'm outlining here, this is the output, equals 14. So I cannot emphasize this enough, how to interpret these kind of statements. So I'm going to go through them one more time. This statement says, when I substitute 10 into the function e, the output equals 8. When I substitute 10 into the function L, the output equals 16. When I substitute 10 into the function q, the output equals 14. Okay, let's look at the next example here. Okay, let's use these functions to calculate each of the following, and then we'll interpret our answers in the context of time and population. In part A, we're asked to calculate the output of the function L when we have substituted 5 into the function. So let's go ahead and do this. Just recall, the L function was the linear function, and I'll rewrite that equation. It was p equals 1.2 t plus 4. So when we are asked to calculate L at 5, we're being asked to calculate the output of this function when the input t is 5. So the output, remember this is how we write output, the output will equal, so we take the 5 and we put it into our function. That means we replace the t with 5. So we get 1.2 times 5 plus 4. Now to calculate this output, we have to simplify the expression. This is where order of operations comes in. Although there are parentheses involved, there are no operations inside. So we proceed to exponentiation, but there is no squaring or raising to powers to be done. So we proceed to multiplication. There's one multiplication to perform. We need to multiply 1.2 by 5. If we multiply 1.2 by 5, we arrive at 6. And so we have 6 plus 4. And now we perform the remaining addition, and we arrive at 10. So when we insert the number 5 into this function, we arrive at an output of 10. Let's interpret this in the context of time and population. T is 5. In other words, we're talking about 5 years out. So in 5 years, this function predicts the size of the population to be 10,000 individuals. Now let's look at part E. Here we're being asked to calculate E at 20. In other words, we want to know what is the output of the function E when we've inserted 20 into the function. Well, I'm going to begin by writing out the equation for the function E. If we recall from the previous page, the equation for the function E was 4 times 2 raised to the t over 10. This is the E function. We are calculating the output of this function when the number 20 has been substituted into the function. So the 20 is playing the role of the t. If I substitute 20 in place of t, this is the expression I arrive at. To simplify this expression, we use our order of operations again. There are parentheses, but again, there is no operation inside the parentheses. So we proceed to exponentiation. We do have to raise the number 2 to a power, but the power needs to be simplified. 20 divided by 10 is 2, so this is really 4 times 2 squared. Now we can perform the exponentiation, or the squaring. 2 squared is 4, so we have 4 times 4, which is 16. Now let's interpret this in terms of time and population. We inserted 20 into this function. The 20 is a t value. It represents 20 years. So in 20 years, the exponential function predicts the size of the population to be 16,000 individuals. Now let's proceed to part C. Here we are being asked to calculate Q at 0. In other words, we want to know what is the output of the Q function when 0 has been substituted into this function. I'm going to begin by writing down the formula or the equation for the Q function. It was given by the equation P equals 0.1 t squared plus 4. Okay, so we are being asked to calculate the output of the Q function when we've put 0 into it. So the output is found by taking 0 and replacing the t with the 0. So we have 0.1. We are squaring t, and t is 0, so we are squaring 0 here. And then we add 4. Now we use order of operations to simplify. Order of operations would stipulate that we perform our squaring first. 0 squared is 0, so we have 0.1 times 0 plus 4. Next we perform our multiplication. 0 times 0.1 is 0, so we arrive at 0 plus 4, which of course is 4. Now let's interpret this. The 0 is a t value, an input value. it represents years. So we're talking about 0 years into the future, which would be effectively right now, I guess. So we're saying right now, or at the current or present time, the function Q estimates the size of the population to be 4,000 individuals. So in this example, you saw how function names are used in the course of evaluating functions. However, a function's name can also be used when we're writing the equation of the function down as well. For example, the 3 functions above, namely the linear function, the exponential function, and the quadratic function, these functions could all have been written as follows, using our new function notation. So instead of using the letter P to represent the outputs of these functions, we could use our new notation for the outputs. So let's look at the first equation. You can tell from the right-hand side that this is our exponential function, and the letter T is the input. So instead of using the letter P for output, I could say E, and then behind it I write T in parentheses, meaning that T is the input. And remember that when we write E at T like this refers to output. So this notation right here, E at T, is exactly the same thing as writing P. E at T and P are the same thing. I want to also remind you that if this is the input, if T is the input, then the letter T has to be on the right-hand side. If I change the letter T to S or R, then I would change my letter in here to S or R. Now let's look at the next equation. You can tell from the right-hand side that this is the linear function above, and instead of writing the letter P for the output, I could write L at T. L tells me that I'm working with the linear function, and I'm inserting the letter I'm inserting the letter T. T is the input, and that agrees with the right-hand side where you see T. Third equation. You can tell that this is the quadratic equation, but I've replaced the letter P with Q at T. The Q tells me this is the quadratic function, and the T in the parentheses tells me that T is playing the role of the input, which agrees with the right-hand side.